Section 7.3 Geometric Sequence and Series. In an arithmetic sequence, a certain number is added to each term to get the next term. When each term in a sequence is multiplied by a certain fixed number to get the next term, the sequence is geometric. In this session, we examine geometric sequence and geometric series. Consider the sequence. We have a 1, 5, 25, 125, and 625. So think about it. If I multiply each term by 5, I'm going to get the next term. So I times 5 here, I'm going to get the 5 here. I multiply by 5 here, I'm going to get the next term will be 25. I times 5 here, that will be the next term, 125. And recall this is the common ratio. Okay, all equal to 5, the common ratio for geometric sequence. A sequence is geometric if there exists a number r called the common ratio. You can use the second term divided by the first term, then you're gonna get the r, that will be the ratio. Or you could use the third term divided by the second term, then you're gonna get the r ratio here. We have the general term an plus 1 equal to an times r. I want you guys to highlight this formula. This is the general term for geometric sequence. Look at this example. We have a 1, 2, 4, 8, and 16. And this is the geometric sequence, which the first term will be the a1. Okay, this is the first term. And then how can we find the common ratio? We're going to use the second term divided by the first term. So 2 divided by 1, we're going to get the 2. Or 4 divided by 2, you're going to get the 2 also. 8 divided by 4, you also get the 2. This is called the common ratio. And then this is the a1 equal to 1, a2 equal to 2, a3 equal to 4. Okay, first term, second term, third term. Okay, this is how we find the common ratio here. Example, I want you guys look at the geometric sequence. Find out the common ratio. So you're going to use the second term divided by the first term. So you're going to get the 6. You could double check, use the third term divided by the second term. It's also equal to 6. So you know the r, that will be equal to 6, the common ratio. B, we're going to use 10 divided by 50. Okay, you're going to get 0.2. Same idea, 2 divided by 10. You also get the 0.2. So the r is going to be equal to 0.2. The nth term of a geometric sequence with common ratio r is given by an equal to a1 times rn minus 1. So highlight this formula. This is going to be your general term for the geometric sequence. Okay, example. Find a5 and an for geometric sequence 6,400, 1,600, 400, and 100. Okay, so first we're going to find the r. We're going to use the second term divided by the first term. You're going to get 1 over 4. Okay, then we want to find the a5, so we're going to plug into the general formula. So a1, that's equal to 6,400. And then the r common ratio, that will be 1 over 4. Plug it in. Simplify it. You should get 25. Okay, now we want to find the general term an. Okay, so plug in a1 and then the r here. You don't need to simplify it. You could just keep this one as your final answer. Okay, example 3. Find r and a1 for the geometric sequence with the second term equal to negative 18 and the fifth term 486. So write down the general form formula. We're gonna plug in A2, okay? A2 equal to negative 18. Okay, that will be equal to negative 18 here. So we could find out the R equal to negative 18 over A1. And then we have the second information here, A5 equal to 486. So plug in A5 to the general term. Okay, and then we're gonna use the substitution. We know R equal to negative 18 over A1. We're gonna plug in here. Use your calculator, find out negative 18 to the power of 4. Okay, the negative gonna goes away because this is an even number, right? And then this is A1 to the power of 4. You cancel one of them. So you're left with A to the power of 3. Simplify it. You should get A to the power of 3 equal to 216. Okay, take the cube root for both sides. So A1 equal to 6. After you find the A1, put it back to the R here. Find out what is your ratio. That will be negative 3. Okay, when the terms of a geometric sequence are added, a geometric series is formed. Same idea, if we add up the geometric sequence, that will become geometric series. Sum of the first n terms of a geometric sequence with common ratio R is given by. So this is the partial sum for the geometric sequence. We do have the first term times 1 minus R to the power of n divided by 1 minus R. And given that R cannot be equal to 1, okay? Highlight this partial sum formula. Okay, find the sum of the first 9 terms of the geometric sequence. So we do have a first term, A1 equal to negative 1, and then n equal to 9 because the first 9 terms. Find out the ratio, so 4 divided by negative 1, which is going to be negative 4. So write down the partial sum formula. Okay, plug it in. Use your calculator for this guy. Negative 4 to the power of 9. And then plus 1. Okay, negative become positive. Simplify it. You're going to get negative 52,429. Okay, example 5. Finding the sum of the first n terms. Okay, we have the first term I equal to 1, and then ending term will be equal to 8. So we could say this is the general form of your geometric sequence. Alright, so we plug it in, you gotta find out this is gonna be your A1 when I equal to 1. And then this is gonna be your common ratio, right? R equal to 5 here. So we're gonna find out the first 8 terms. Okay, so n equal to 8, plug it in, simplify it. Okay, infinite geometric series. Suppose we consider the sum of the terms of an infinite geometric sequence, such as 1, 5, 25, 125. We get what is called the infinite geometric series. When we add it up and with the dot, it's going to be going forever. This is called infinite geometric series because we're adding it up. Here, has n increased, the sum of the first n terms, Sn, increase without bound. Okay, it's going to be getting bigger and bigger for the number. And there are also infinite series that get closer and closer to some specific number. Here is an example. Note as n gets larger and larger, the value of Sn gets closer to 1 over 4. We say that 1 over 4 is the limit of Sn. And that 1 over 4 is the sum of this infinite geometric series. An infinite geometric series is denoted as infinity. It can be shown that the sum of the terms of an infinite geometric sequence exists if and only if when the R is going to be less than 1. Okay, R has to be less than 1. Remember the session 7.1? We talk about that when the n is getting larger and larger, and then the partial sums is going to be increasing without bounds. We call this is going to be divergent. But when your n is getting larger and larger, but the partial sum gonna get close to a real number, then we say that this is gonna be convergent. Okay, it will be converged to a certain number. And this example, when n is getting larger and larger, you could see the partial sum is gonna be gets closer to the 1 over 4. Okay, so we're gonna say this is gonna be converged to the 1 over 4 here. But then we do have the restriction for with geometric sequence. The R, the common ratio, has to be absolute value of R strictly less than 1. Okay, it has to be strictly less than 1. When the absolute value of the R is strictly less than 1, the limit of an infinite geometric series is given by, we do have this formula highlighted. Okay, as infinity, that will be equal to the first term, A1 over 1 minus R. Okay, and keep in mind the R has to be less than 1 here. Okay, R has to be less than 1. Determine whether each series has a limit. If a limit exists, find it. So first, find out the ratio. What is your R equal to? We can use negative 12 divided by negative 2, which is going to be 6, right? So the R is not less than 1. So you know the series does not have a limit. Okay, the number is going to be getting bigger and bigger. Okay, B. Use 10 divided by 50. So the R will be 0.2. Okay, so 0.2, which is going to be less than 1 here. So you should see as n getting larger and larger, the number is going to be converged to a number. Okay, so we should be able to find the limit. So we're going to use the S infinity formula. Okay, we're going to plug it in. A1, that will be equal to 50. And then the R, that will be 0.2 here. Plug it in. You're going to get 62.5. Means when the n is keep increasing, then the limit is going to be tends to 62.5. Okay, this one. Find out what is your A1, what is your R. This guy, that will be the A1, right? And this is going to be your R here. Okay, so this is good. The R is less than 1, right? Strictly less than 1. So we should be able to find the limit. Plug it into the formula. You should get 3 over 10. Okay, last example. A1, that would be equal to 0.9, right? And then the R is also equal to 0.9. So 0.9, that's a strictly less than 1. So we could apply the formula. Plug it in, you're going to get the 9. That's it.